This is the next video in a chapter on advanced theories of bonding. We are going to talk about the first kind of hybridization, which is called Sp3 hybridization. So you'll know that you need to use Sp3 hybridization if your central atom has 4 electron groups around it. So let's use water as an example, so we can prove that we can improve valence bond theory by including hybridization. The Lewis structure of water shows that there are 4 electron groups. 2 of them are bonding groups holding hydrogens. 2 of them are lone pair groups. And oxygen is our central atom. So this is the one we're going to need to hybridize. Because that oxygen needs to have 4 equal shape, equal energy orbitals to use to hold on to those 4 groups. 1, 2, 3, 4 electron groups to hold on to. So we're going to talk about the orbitals, the shape, the energy, and the sigma overlap for this type of hybridization. Let's start by talking about which orbitals we need to blend together. So oxygen has 4 valence orbitals. It has an s orbital, and it has 3 p orbitals, and that valence shell. And since we need to hold 4 electron groups, we need to blend all 4 of these valence orbitals together. This isn't always true, but for this first type of hybridization, we will blend all of the valence orbitals together. So when we put those 4 orbitals into the hybridized machine, what comes out are 4 identical orbitals that are 25% s and 75% p. And so to represent that, we call them sp3 orbitals. 4 atomic orbitals went in, 4 sp3 hybrid orbitals come out. And these are our new hybrids. And so each of these hybrid orbitals is going to be 25% s character and 75% p character. So those are going to be the names of the orbitals. Let's move on to the shape. We said we wanted the shape of those orbitals to be the same, but what shape exactly is an sp3 orbital? Well, let's look at what orbitals we mixed in, and then we'll look at what sorts of shape comes out from that. So we're pretty familiar with the shapes of these atomic orbitals by now. We know that the s orbital is spherical, and those 3 p orbitals, the px, py, and pz, look like 2 balloons tied together, one on each axis. So when we hybridize these 2 different shapes, we're going to get a shape that looks a little bit like both of them, and we're going to get 4 copies of it. And each of the 4 copies, similar to the p orbital, which lie on a different axis, each of these new sp3 orbitals is going to point towards a corner of a tetrahedron, or a 4-sided shape. So I'm going to attempt to draw 4 tetrahedra with their center point. Best of luck out there drawing them on your own paper. Okay, that's going to be our best go. So each of these hybrid orbitals is going to start at the center, and it's going to point at one of the tetrahedron points. And it's going to have 2 lobes, similar to a p orbital, but similar to an s orbital, only one of those orbitals' lobes is really large enough to make a difference. So we have a lobe pointing towards the bottom left corner. We have another one pointing towards the front corner. We have one pointing towards the front right corner, and one pointing towards the top corner. Let's do a zoom in on that because it can be a little bit difficult to see in that small picture. So each of these sp3 orbitals has a larger lobe and a smaller lobe. The larger lobe points straight at one of the corners, and the smaller lobe points 180 degrees away from that. But this larger lobe is so much larger than the other side that it's the only one that we ever actually draw. Most of the time we leave out the smaller lobe because it makes the picture too crowded. So let's do that. Let's leave out the smaller lobes and draw all 4 of these sp3 hybrid orbitals on one big tetrahedron. We have one large lobe pointing towards each corner, and each of those are going to be separate sp3 orbitals. Don't be fooled by the 4 lobes in the picture to think that this is a d orbital. These are each a single lobe from a different sp3 orbital. There are 4 orbitals here, and those lie at the correct angle to make an electron geometry of tetrahedral, which is the geometry that we know H2O should have, with an angle of around 109.5. So these are the shapes that we expect to see that come from that hybridization. And we also need to consider the energy of those hybrid orbitals, because after all, that's one of the main reasons we decided to hybridize them. So let's draw the valence orbitals for oxygen. We've got our 2s and our 2p. And we know that we need identical energy orbitals to hold 4 electron groups. So we need to blend all 4 of oxygen's valence orbitals together. So we'll circle all of those. Then we will throw them in our hybridized machine. And what comes out are 4 hybrid orbitals that have an energy that's intermediate to the energy of the 2p orbitals and the 2s orbitals, drawn here by my dashed lines. So remember that these sp3 orbitals are 75% p and 25% s. So they are 75% of the way to the p orbital and 25% of the way to the s orbital. So they are going to be approximately 3/4 of the way towards the p orbital in the picture. So we had 4 atomic orbitals went in and 4 hybrid orbitals came out with an intermediate energy of the 2 that went in. So let's draw our Lewis structure for the water again. And this time we can indicate a little bit more clearly which orbital is being used to hold each of those different electron groups. I'm going to use dots to represent my atoms so it's a little bit less crowded in this picture. So we've got the 2 hydrogen atoms, the oxygen atom, and 2 lone pairs. The hydrogen is the easiest one to start with. Hydrogen only has 1 valence orbital, so it will always choose its only 1s orbital for bonding. And then our oxygen is going to be sp3 hybridized. So pointing towards each of those hydrogens is going to be an oxygen sp3 orbital. And that overlap is going to create the sigma bond. The other 2 sp3 orbitals are going to be holding the lone pairs. Because lone pairs are not atoms, they do not have orbitals. They are just electrons that need to live in a particular orbital from oxygen. And so our 2 sigma bonds between the oxygen and hydrogens are formed between a hydrogen 1s and an oxygen sp3 orbital. In the next video, we'll talk about the next type of hybridization, which is called sp2 hybridization.